In this video, we continue with the computer science A-level curriculum, taking a look at Dijkstra's algorithm. Let's go ahead and jump into the learning targets to know what we're looking for. So candidates should be able to. They want us to be able to show an understanding of how graphs can be used to aid artificial intelligence. So they want us to know the purpose and structure of a graph, how to use the A-star and Dijkstra's algorithms to perform searches on a graph, that we are not required to write algorithms to set up, access, or perform searches on graphs, but we got to know how they work. So let's go ahead and get started. So what is a graph in computer science? Well, a graph in computer science is not like the graphs you see in science or math class. Each graph in computer science is made up of a set of points. Now, each point, we call a point, a node, or vertex. They use these terms all the time. They interchange these terms, so you got to know all three of them mean the same thing. Now, the distance between two nodes or vertices is known as distance or edge. They are a fundamental part of artificial intelligence. Now, graphs are used in GPS programs like Google's app Maps. Ever notice how when you use maps, it shows you the fastest route compared to other routes you can take? It may also say you're on the fastest route to your destination. Well, this is because of graphs. Now, when it says you're on the fastest route to your destination, that's specifically using the A-star algorithm, which we'll get into in the next video. So what do graphs look like? Well, they look like this. I just looked for a map online. This one came up and it was small. It allows us to easily see how to implement Dijkstra's algorithm. Now, our starting point is going to be A, and we're going to be looking on how can we get to D using Dijkstra's algorithm, and how can we make sure it's the smallest pathway. So let's take a look at Dijkstra's algorithm. It's a method that is used that can find the shortest distance between 2 points, nodes, or vertices. So remember how I just mentioned the Google's Maps app? Well, it's also used when you're sending data over the internet. This is used for directing the data to the next node. Otherwise, your data would be bouncing all over the place repeatedly and possibly not make it to the destination at all. We talked about that earlier in the year when we did the difference between circuit switching and packet switching. And this is describing packet switching. Now, there are some items each vertex, node, point, whichever one they're going to use, needs, and you must become familiar with each of them, and that is the key to success with Dijkstra's algorithm. So we're going to go ahead and go over the terms, and then we're going to apply them. So let's take a look at the terms. You need to know vertex letter. Now, this is simply a letter representing a node. We also have a term called a working value. Now, this is a temporary value given to a node that you use to work with, which could become its final value. Now, the final value given to a node used in determining the shortest path between two nodes. We also have an order of labeling. This is a value given to a node representing when it was ordered, and the layout usually looks like this. I say usually, it's formatted like this for a reason. So in the upper left, we're going to have our vertex letter. In the middle, the order of labeling. That way we know which box or node or vertex or point to do next. We have a final value which says, hey, our node is done, and we have our temporary working value. So let's go ahead and let's draw out our map. Our graph, which could be a map. So here is our graph that we had right here. What I need to do is I need to draw it using the format that we have. So I'm going to draw A with the format we have. I'm going to draw B. I'm going to draw C. I'm going to draw E. And I'm going to draw D. Now I could draw these in any order, but I need to make sure that it matches our graph here. Now that it matches our graph, I can take a look at the steps. Now each step is going to be broken down, and we're going to update the graph as we go to make this as simple and as easy as possible to understand. Remember, we're using the Dijkstra's algorithm to solve the shortest path between two nodes. So step 1, we give the start node a final value of 0 and a labeling value of 1. So in our graph, A was the start node. So you'll see that our order of labeling was 1. We give it a final value of 0. And just like that, A is done. Now let's move on to step 2. We give each node connected to the node that just got a final value a working value. So let's back up. A just got a final value. So now we have to give B and we have to give C a working value, which will go right here in these bottom boxes. So now, here's the important thing to remember. If the node already has a working value, we replace it with another, but we only do this if the value is lower. So right now, B and C do not have a working value, so we don't have to worry about that special rule right here, but we're going to go ahead and add the working value. But where do I get the working values? How do I know what they are? Well, it is the distance from the node you are on to the one you just gave a final value to. So the working value for B is the distance or edge from B to A. The working value for C is the distance or edge from C to A. But which one do I work with first? B or C? Well, this is why we have the labeling value. We work in the order of the labels. So B has a lower labeling value. I'm looking in this top middle box here than C does. So B was given a label value of 2, C is 3, D is 4, E is 5. We used it in the order of letters. So I gave it a value of 4. But where did this working value for B come from? Remember, it came from the distance or edge between node A and node B. So we're still on step 2. Remember, if the node already has a working value, replace it with another, but we only do this if the value is lower. So now that we've done B, it's time to do C. C has a working value of 5. Where did I get this from? It is the distance or edge from A to C. It is that simple. So we move on to step 3. We check the working value of each node not assigned a final value. We assign the smallest working value as its final value. Now, A has already been completed. B and C right now are the only ones with a working value, so we need to go ahead and set a final value for them. Now, how do we set their final values? Their working values become their final value. Let's go ahead. Let's update our graph. So we can see our final value for B is 4, and that is because our working value was 4. Now, just so you know, if we had another node coming in to B, whatever the smallest value would be between whatever this extra node is, if the distance, say, was 2, we would replace this working value with a 2 because we're looking for the smallest working value. Because there's only A coming into B, we're going to give it the smallest working value. So C has a final value of 5. So we repeat steps 2 and 3 until all nodes have a final value. Don't forget, we still have E and D out there. So step 2, give each node connected to the node that just got a final value, a working value. Remember, the node already has a working value. We replace it with another, but we only do this if the value is lower. Step 3, we check the working value of each node not assigned the final value. We assign the smallest working value as its final value. Now, we just did B. We just gave B a final value. So let's work with item C. But C already has a working value and a final value. If a node already has a final value, it can be ignored. It does not get reworked again. So there are 2 nodes connected to C. They are E and D. Let's go ahead and let's give them a working value. But wait, the working value must include the working value of the node we are going from. We have to add that in because we're not just going from C to D or C to E. We're going from A to C to D, from A, C to E. So we take the final value of C and we add it on the distance or edge from C to D. So let's take a look at what this looks like. So here's E. I do 5 plus 6. I notice I have my value of 6 from C to E, but what is the final value of C? 5. 5 plus 6 gives me a working value of 11. And for D, I have 5 plus 3. My final value of C plus the distance from C to D, which is 3, that gives me a temporary working value of 8. So no other nodes connect, so we have the smallest working value for D and E. Let's go ahead. Let's assign the final value. So we know that we had the temporary working value of 11. We had the temporary working value of 8. So we have 11 and we have 8. It is that easy. And now we are almost done with Dijkstra's algorithm. So step 5, trace the route back from the end node to the starting node. Now remember, we said our final node was D. This is what I selected for the video. There's no formula for that. If you're wondering, how did I get D as my endpoint? That's just what I selected for this video. There's no formula to determine the endpoint. D is just what I selected. So here's what our graph looks like. Now, because our graph's so small, it's easy to do the last step. We can see from A to C, we have a distance of 5. From C to D, we have a distance of 3. Another way I could take is A to B to C to E, but that's not the shortest path because I got to go 4, then I got to go 7, which is 11, then 3, which is 14. So I can see that is not the shortest path. So the last step is easy because our graph's so small. But what if our graph was large? Do we just use the process of elimination? Well, you want to follow this simple rule, and if you follow this rule, you'll always find the shortest path. If the distance of a path is equal to the difference between the final values of two nodes, it is part of the shorter path. And you may be saying, okay, slow down, let's read that again, and let's see it in action. If the distance of a path is equal to the difference between the final values of two nodes, it is part of the shorter path. So let's take a look in the action. So D, we know we have to go D to C because that's the only option. How do we know we did this correctly? Because we're looking for the distance between two nodes. So I have the value of 8, I have the value of 5. We said the difference between those two nodes. What is the difference between 8 and 5? 8 minus 5 gives me the value of our distance, which is 3. So I know D to C is part of the shorter path. Now, if I try to go from here, say maybe C to B is the shorter path. Well, if I check C to B, 5 minus 4 is 1. That is not equal to 7. So I know that is not part of the shorter path. So I check C to A. Maybe that's part of the shortest path. How do I determine that? I take the final working value of C, which is 5, the final working value of A, which is 0. I find the difference between them. 5 minus 0 is the value of 5, which matches the distance. I hope you found this video helpful. If you did, please give a thumbs up and subscribe. If you have any comments, please post a question below or a comment below. And we'll see you guys in the next video.